Hi class, so let's learn combined loadings. Today I will discuss you the thin-walled pressure vessels. First, what is the pressure vessel? A pressure vessel is a container designed to hold gases or liquids at a pressure different from the surrounding environment. So when we say thin-walled pressure vessel, a pressure vessel is considered thin-walled if the radius is greater than or equal to the 10 times of its thickness. So, meaning class, mas manipis po yung wall compared sa radius. Kaya we assume that the stress is uniform across the thickness. There are two main stresses acting on the vessel. The first one is the longitudinal stress or the axial stress. Ito yung stress na along the length of the cylinder. It resists the force trying to split the cylinder into two parts lengthwise. Usually, smaller po siya compared to hoop stress or the tangential stress. So we have the formula for longitudinal stress equals to P R all over 2T, where the the sigma sub L is the longitudinal stress. Then P is the internal stress, internal pressure. Then R is the radius. Then T is the thickness. Okay? So yung important note to remember po is that longitudinal stress is half of the hoop stress. Then let's move on to the tangential stress, or also known as hoop stress. For longitudinal, it is also known as axial stress. So yung longitudinal stress po, nag-act siya dun sa thickness ng thin-walled vessel natin. While sa tangential stress, nag-act siya dun sa circumference ng thin-walled vessel natin. For the tangential stress or hoop stress, ito naman yung stress around the circumference ng cylinder. So it resists the force that tries to burst the cylinder open. So this is the critical stress, and usually mas malaki siya sa longitudinal stress. So we have the formula for the tangential stress equal to PR over T, where P is the internal pressure, R is the radius, and T is the thickness. Then the sigma sub H is hoop stress. Yung key idea naman po sa tangential stress is that hoop stress is twice the longitudinal stress. So ito ang mas dangerous. So aside from the formula that I gave earlier, where the tangential or the hoop stress is equal to PR over T, you can also use this formula in terms of diameter. Pag ang given na dimension is naka-diameter, just substitute the radius to diameter. What is the radius equal to diameter? So D over 2. Therefore, if you are going to substitute the D over 2 in our formula, we get this 1. Then same goes with the formula of the longitudinal stress, PR over 2T. So just substitute the radius to diameter. The radius is equal to half of the diameter, 2T. So to simplify our equation, 2 times 2 is 4T. So same with our derived formula. So let's solve a problem. A cylindrical steel pressure vessel 400 mm in diameter with a wall thickness of 20 mm is subjected to an internal pressure of 4.5 MPa. Calculate the tangential and longitudinal stresses in the steel. For part B, to what value may the internal pressure be increased if the stress in the steel is limited to 120 MPa? To solve for the tangential stress, we'll use the formula PD over 2T, where P is equal to 4.5 MPa. Then the diameter given is 400, then the thickness is equals to 20. Take note class, pressure is in MPa, kPa. So yun po yung mga unit ng internal pressure. So we'll get a tangential stress equals to 45 MPa. For the longitudinal stress, basically it is half of the tangential stress. will get 22.5 MPa. Next, for part B, to get the internal pressure with the increase of stress equals to 120 MPa, we'll only check the tangential stress kasi siya yung critical dun sa dalawa. So, substituting tangential stress equals to 120. So, this is the solution for part B. The unknown P times the diameter equals to 400 over 2 times the thickness 20 will get an internal pressure equals to 12 MPa. So that's our solution for part B. Next, for sample problem number 2, a water tank 6 meter in diameter is made of steel plates 12 mm thick. Find the maximum height to which the tank may be filled if the circumference stress is limited to 110 MPa. The specific weight of water is 9.81 kN per meter cube. So, pinapahanap dito class yung maximum height ng tank given with the circumferential stress. Pag sinabi nating circumferential stress, it is the tangential stress or the hoop stress. Or tangential stress sigma sub T. So, use our formula PD over 2T. So, we can solve the internal pressure equals to 0.44 MPa. Since yung diameter natin naka-meter, para uniform yung unit natin, kinonvert natin siya to mm, kaya naging 6,000 mm. Then, yung thickness natin is in 12 mm. So, yung nakuha nating pressure is naka-MPa. Pero since maliit siya, i-convert natin siya sa kilopascal. Kaya magmumultiply ka ng 1,000 para yung magiging unit nito naka-kilonewton per meter squared. So, 440 kPa yung nakuhang internal pressure. Next, para makuha natin class yung depth or yung height ng water. So, meron tayong formula for internal pressure pag may liquid, specifically, ang laman niya is water. So, it has a specific weight equals to 9.81. So, ito yung ginagamit nating variable. Minsan, may makikita din kayong lambda as a specific weight or specific unit weight. So, yung solution natin, pag pressure, since ang unit ng specific weight natin is in kilonewton cubic meter times the height. So, ito makakancel out. Matitira is meter squared. So, kilonewton meter squared is equal to kPa. So, 440 equals to 9.81. Yung makukuha mong height is meters. So, meron tayong result na 44.85 meters. In our previous topics, we learned how to determine stress when a member is subjected to only one type of load, such as the axial force, the shear force, bending moment, or torsional moment. But in a real-life engineering situations, hindi po lang isa ang load na ina-apply. So, most structural members experience multiple loads at the same time. So, what is combined loading? Combined loading happens when a member is subjected to two or more types of loads simultaneously. So, example, a beam can experience bending and shearing. A shaft can experience torsion and axial load. Then, to solve this, we use the principle of superposition. So, this means we compute the stress caused by each load separately, then add them together to get the total or resultant stress. In simple terms, class, iniisa-isa natin bago pagsamahin. So, however, However, may important condition tayo dito. Yung geometry of the member should not change significantly when loads are applied. So this means small deformation only and linear behavior or nasa elastic rin siya. So bakit siya important? Because it ensures that the stress from one load is independent of the other. So valid ang superposition method. Okay. So let's have an example to solve or to apply the concept of superposition for the combined loadings. So the member shown in has a rectangular cross-section. Determine the state stress that the loading produces at point C. So first step is kunin yung mga reaction at the support. Since ito is hinge support, may dalawa tayong reaction na kukumputin, the vertical and the horizontal component ng reaction at support support A. Then meron tayo ditong roller. Then meron siyang one reaction at support B. Then may given ditong uniformly distributed load. Para makuha natin yung resultant niya na nasa gitna, i-multiply natin yung uniform load 50 kN per meter sa 2.5 para maging resultant yung uniformly distributed load na equal siya sa 50 times 2.5 equals to 125 kilonewton. Okay, so let's have the solution for the reaction at support B. So kukuha tayo ng reaction at support B pag nag-take a moment tayo sa support A. Okay, since naka-incline yung hindi siya yung typical na horizontal or vertical na reaction or forces na nag-act dun sa system natin, we need to break it to horizontal and vertical component. So dito, meron tayong vertical and horizontal component. So, makukuha natin class yung relationship ng small triangle dito galing sa big triangle. Basically class, this is a 3, 4, 5 na small triangle. Kasi pagka dinivide mo yung 2, yung 1.5 dinivide mo sa 2, yung ratio niya is equal to 3 is to 4. Then yung hypotenuse naman niya, since yung vertical is 3, yung horizontal is 4, so yung magiging hypotenuse niya is 5. So ito yung 3, 4, 5 na triangle natin. Same with this one. So, meron din tayong small triangle na 3, 4, 5. Okay. So, yung magiging component ng vertical at reaction B. So, vertical dito based dun sa triangle. Yung vertical niya is 4 is to 5. 4 over 5. Then, yung horizontal naman niya is RB times 3 is to 5. Then, dito naman may horizontal and vertical component din to. So, RW, yung horizontal niya is 3 over 5. Then, yung vertical component, 4 is to 5. Okay, so solve natin yung reaction at B, where we are going to take a moment at point A. So, positive yung mga clockwise direction. Meron bang clockwise direction dito? Clockwise. So, ito clockwise. Ito din clockwise. Itong horizontal and vertical component ng B, parehong counterclockwise. So, yung R, W natin, or yung resultant ng uniformly distributed load. So, para makuha natin yung moment arm niya, pag moment arm, always siyang perpendicular dun sa reaction natin. So, yung kalahati ng 2.5 is equal to what? So, 2.5 divide 2 is 1.25. So, nag-act yung resultant ng uniformly distributed load sa gitna ng 2.5 or length niya. Length niya is 2.5. 1.25, I mean. Ito yung 1.25. So, ano yung magiging moment arm ng vertical component ng uniform load? So, nasa gitna siya. So, kailangan natin kunin itong horizontal ng 1.25. So, ano yung horizontal ng 1.25? So, 1.25. So, gagamitin lang natin yung triangle 3, 4. So, kukunin natin yung ratio ng 4:5 para makuha, I mean the horizontal. 3, 4. So, horizontal ratio ng 1.25, 4:5 is equal to 1. Yung vertical niya. So, yung height nito is 1. Ayusin lang natin. 1.25, 1.25. Then may triangle dyan. Small triangle. 3, 4, 5. So, para makuha mo yung horizontal ng 1.25, kunin mo lang yung ratio. Ito yung 1 meter. Na kailangan pa natin i-add yung 4 meters kasi magmo-moment arm tayo dito sa point A. So, 5 meters yan. So, times 5. Then, plus yung horizontal component ng uniformly distributed load. Yung moment arm nyo naman is, ito yung horizontal. Then, yung moment arm nyo is perpendicular. Kukunin lang natin yung height ng 1.25. So, basically, kunin mo lang yung ratio ng 3:5 na. So, 1.25 is equals to 0.75. 0.75. Then, minus na natin yung mga opposite doon sa assume positive direction ng moment natin. So, equal na natin siya para maging positive. So, RB, then yung vertical component niya is 4:5 times yung moment arm niya, since ito yung vertical component, yung moment arm niya is perpendicular distance na 6 meters. Plus yung horizontal component 3:5. Then yung moment arm niya naman na perpendicular dun sa saan? Dun sa point A. So meron siyang height na 1.25, 1.5. So para makuha natin, so substitute na natin tong value na 125, ito 125. So para makompute natin yung value ng RB, 25 times 4/5 times 5 plus 125 times 3:5 times 0.75 is equal to RB 4/5 times 6. So yung nakuha nating sagot for the RB is equal to 97.59 kilonewton. So yan yung resultant or reaction at point B. Okay. Equals to 97.59. Then para makuha naman natin yung horizontal and vertical reaction at point A, so mag-summation forces horizontal lang tayo and vertical forces. So sa vertical, meron tayong unknown RA sub Y. Then pareho yung direction ng RA sa component ng RB. So plus din yan. So yung RB times 4/5. Then may isang opposing direction ng vertical component minus RW 4/5 is equal to 0. Ito, value niya is 125. Yung RB natin is 97.59. So, yung value ng vertical component or reaction at point A is equals to 97.59. 4/5 minus 125 times 4/5 is equal to 21.93 kilonewton. Then, summation forces horizontal equal to 0. So, kukunin naman natin yung sum ng lahat ng mga horizontal forces. So, meron tayong RAX plus yung horizontal component ng RB. So, same yung direction niya sa RAX. So, addition din natin. Minus RW 3/5 equals 0. So, ito, ang value niya is 125. Ito is 97.59. So, yung value ng RAX natin is equal to plus 97.59 3/5 minus 125.3 over 5. So yung nakuha natin is 16.45 kilonewton. Okay, next. Next, so kunin natin yung mga internal resultant at point C. Ibig sabihin ng internal resultant, yung normal force, shear force, at saka yung bending moment. So para madali yung solusyon natin, gagamitin na lang natin ng bisection method. So, magkakat lang tayo dito sa may bandang kung nasaan yung point C natin. Section ng point C. Then, meron tayong mga reaction sa point A. So, yung nakuha natin horizontal, 16.45 kilonewton. 16.45 kilonewton. Then, yung vertical reaction niya is 21.93 kilonewton. Para makuha natin yung normal force, since wala nang iba dyan na horizontal, so mag-equate lang siya na dito sa cutting section natin at section C. So, equals din siya sa 16.45. Ito yung normal force natin equals to 16.45 kilonewton. Then, yung shear naman dito at point C. So, yung shear natin is yung oppose niya yung vertical upward na force na to. So, yung nandito sa cutting section natin is because of 21.93 kilonewton, but this time to maintain equilibrium, so downward yung direction. Then for the bending moment, so meron tayo dito distance ng point C sa point A na 1.5 meters. So para makuha natin yung bending moment, so mag-moment lang tayo at point C. Then yung moment niya, since positive yung counterclockwise pag nag-cut ka, ito yung moment. So, yung moment dito is equal to 21.93 times the moment arm na 1.5 is equal to, so equals to 21.93 times 1.5 equals to 32.89 or 90. 32.90 kilonewton meter. Then, may cross-section tayo na in rectangular shape. So, magkakaroon tayo dito ng normal stress distribution. Pag normal stress distribution, so kukunin lang natin yung P over area. So, distributed siya evenly throughout the cross-section. Ito yung normal stress distribution natin. Then, for the shear stress distribution natin, pag rectangular, nasa na yung, okay. Pag rectangular class, sa shear, kung nasa yung neutral axis, nandun yung maximum. Pero, yung nasa uppermost at saka nasa lower part ng cross-section natin, 0 po yung shear natin. Gawa nga na yung Q dito is, yung area dun sa Q is equal to 0. So, yung shear dito basically is equal to 0 or yung FB dun sa may edge. Kasi, pinapahanap dito klase yung shear at a specific point dito sa C, at point C. Then, yung behavior ng shear, so, para mag-slide siya pababa. So, yan yung shear natin. Then, for the moment or bending stress naman, so, kabaliktaran siya ng shear. So, yung outer or uppermost at saka lower part ng cross-section, nandun makikita ang maximum maximum bending stress. Kung saan yung upper fiber ng neutral na nasa neutral axis is compression yung nararanasan. Ito naman yung bending stress. So, sige. So, solve natin class, yung normal stress is equal to force over the area. So, yung force dyan, pag sinabi natin normal, tumatama siya perpendicular dun sa cross-section. So, sa nasolve natin, yung normal force dito is 16.45 over yung area ng cross-section natin. Meron siyang dimension na 50 by 250 mm. Tama ba? 250 by 50. So, 50 times 250. Since naka kilonewton yung unit nito, kailangan natin siya i-multiply sa times 3 para maging MPa yung makukuha nating unit. 16.45 times 10 raised to 3 over 50 times 250. So, 1.3 or 32 MPa yung normal stress na nag-a-act in compression. Kasi nga, paloob po yung force natin. So, ito yung force. So, compression, negative po yung sign natin. Then, for the shear naman, yung shear natin is VQ over IB. Since yung Q dito is area prime times Y bar prime. Since wala ka dito i-consider na area dun sa tuktok, so yung area mag-equate siya sa 0. Basically, yung Q natin is 0. So, anything that multiplies with 0 mag-equate sa 0. So, 0 yung shear natin sa topmost fiber. Then, sa bending naman natin, bending stress is equal to MCI, where yung moment dito na compute natin is equal to 32.90. And naka-kilonewton meter, so kailangan natin ito i-convert to newton, mm. So, kailangan mag-multiply pa ng 10 raised to 6. Then, yung C natin is yung distance niya from the neutral axis papunta dun sa location ng point C na nasa gitna ng kung saan yung neutral axis is nasa gitna. So, kalahati ng 250 is 125 mm. Over yung moment of inertia ng rectangular section natin is equal to base times the height, base times the height raised to 3 over 12, or yung moment of inertia ng rectangular section BH cube over 12. So, yung makukompute natin, 32.90 times 10 raised to 6 over, times 125 over 50 times 250 raised to 3 over 12 is equal to 63.17 MPa. Since nasa topmost fiber yung pinapahanap na bending stress, so nasa compression side siya. So, ito, lalagyan natin siya ng C to indicate na negative po yung bending stress. Then, para makuha natin yung combined stresses at point C, kunin lang natin yung sum ng lahat ng stresses na nag-a-act dito sa cross-section natin. So, 1.32 plus 0 plus 63.17. So, yun yung importante dito sa pag-determine ng kung compression siya or tension, kasi dyan depende yung sign convention mo. Pag compression po, negative talaga siya. Pero since kunin lang natin, same lang yung dalawa, kunin lang natin yung sum ng bending at saka ng normal stress. Then, saka na lang natin i-change yung sign nila. So, 64.49 MPa. So, negative siya to indicate na compression, or pwede mo din na isulat as 64.49 MPa indicated na may sign siya ng C. So, compression siya. So, ito yung solution natin for this problem. So, ito yung sagot natin. Okay, last item. So, let's solve this one. A force of 150 pounds is applied to the edge of the member shown. Neglect the weight of the member and determine the state of stress at point B and C. So, pinapahanap class yung the state of stress at point B at point C. So, as you can see here, meron tayo ditong force na hindi nag-a-act dun sa saan? Hindi siya nag-a-act dun sa centroid ng cross-section natin. So, magkakaroon to ng effect sa cross-section yung bending moment niya at saka yung normal stress. Para makuha natin class yung bending moment, so pwede natin equate yung bending moment sa M is equal to P times E. So, ibig sabihin, hindi nag-a-act sa centroid yung force. So, meron siyang bending moment gawa no eccentric distance na 5 inches papunta dun sa neutral axis. So 150, yan yung force natin. P is equal to force times the eccentric distance from the neutral axis na 5 inches. So makukuha natin is 150 times 5 equals to 750 pounds inches. So yan yung moment natin. Next is i-determine natin yung moment of inertia. So BH cubed over 12. So kadalasan, yung height dyan yung pinakamalalim, which means yung cross-section na to, yung cross-section niya is 4 by 10. So yung base niya is 4 times the base na, times the height na 10 cubed over 12. So yung moment of inertia nito is 4 times 10 over 12 is 333.33 with the repeating 3 inches raised to 4. Next, so may dalawa ditong stresses na nangyayari, the normal and the bending moment. So ito yung kailangan nating hanapan ng state of stresses. So kung hahatiin natin yan, yung nararanasan nito, example, ito na yung yan. Okay. So example, yan. So para makuha natin class yung normal stress, yung gagawin nyo lang is kukunin natin yung force over area. So tatandaan nyo, yung force po, yan din yung nararanasan niya dito sa ilalim. Since nag-act siya in compression, syempre, ika-counteract siya dito sa baba na in compression din. So yung force na mararanasan din sa baba is 150 pound over yung area na 10 by 4. So equals to, nasa yung calculator, 150 over 10 times 4 is 3.75 PSI or pounds per inch squared. Then take note, compression siya. Next, for the moment naman po, so magkaiba yung nararanasan dito na moment sa moment dito sa C. Kasi yung moment na nasa C, nasa compression side siya. Ibig sabihin, pareho yung magnitude ng dalawa kasi pareho sila sa dulo, pero ang pinagkaiba lang yung sign nung nasa point C kasi ito, ang mararanasan dito sa ilalim is compression. No? Kung nasaan tumatama, yung tatandaan nyo lang, kung nasaan tumatama yung force, nandun yung compression side. Then dito, ang nararanasan niya is tension. So ito is normal, ito is bending. Gagamitin natin yung general formula ng bending, MCI. Yung moment natin is 750 times yung distance from the neutral axis papunta dun sa location ng point B at saka point C. Since pareho silang 5 inches, so same lang yung magnitude, pinagkaiba lang po is yung sign ng point C at saka point B. Then yung moment, the moment of inertia naman natin is 333.33 with the repeating 3. So yung makukuha natin 750 times 5 over the moment of inertia equals to 11.25. Positive or negative. Pero dito, negative yung compression natin sa normal stress. Okay? Next. So ano yung state? Ito is bending. No? Bending po to. Hindi yung moment talaga ng, the state stress at point P. So bending siya. Ito for bending stress, ito naman is for normal stress. So, inalis ko muna yung subscript para hindi kayo malito dun sa pinapahanap na state stress at point B at point C. So, para masolve natin yung point B, so negative yung normal. So, kukunin lang natin yung sum ng dalawang stresses. So, sa point B, pareho lang yung nararanasan dito na normal stress, in compression pa din yan, kahit saan dyan. Kasi even it is distributed po yung normal stress, gawa nga na kinukuha lang natin yung ratio or yung force over the area dito sa entire section. So normal, then lagyan na lang natin ng bending stress, y na lang. So, dito sa point B natin, ang nararanasan, ito yung neutral axis. Nasa baba po siya ng neutral axis. So, ibig sabihin, ang nararanasan dito is the tension. So, positive. Then, sa C naman, negative pa rin yung normal. Then, negative yung bending stress kasi nandito banda nararanasan yung compression side. So, kung ititrace natin, tumatama yung point C dun sa compression. So, yung normal is negative 3.75 plus 11 talagyan natin ng unit, 25 PSI. So, yung makukuha nating sagot for this stress at point P, 0.5 PSI. Then, for stress naman at point C, negative 3.75 minus 11.25. So, we get negative 15 PSI. Ito, yung tension kasi positive yung lumabas. While si stress at point C, 15 PSI compression. So, ito na yung final answer natin, class.